See my screen?
Yeah, I can see.
Okay. So what we'll design a universal counter. Okay.
Okay.
What we are looking like, what it should do, features like it can increment, and decrement, and can load any value, right? Whenever you want, like we can start a counter, like let's say we load a value, let's say some value, and then from there you can count decrement or increment. Okay.
Okay.
Fine. Then, so if you are looking like this, these three features, how our like design, like ports look like, what we need. We need till now what will it's a counter, right? So you can guide me like what will be the ports or what will be the control to the counter.
I think
There were two things. Since it's a sequential circuit, so there's a clock needed
yeah,
and there's a reset needed. Okay.
this.
And definitely we are loading, so we should have a load enable, load basically load input. Okay, load enable, and then there'll be a enable also, right?
Enable.
When we enable, then it will increment or decrement. And then one will be what? The load value. We can load a value, right? Which value should start, so we can have a load value. And the other input, increment or decrement. Okay, so when we can say when it's a 1, it's increment; when it's a 0, it's decrement. And there will definitely one only output, which is like count. Okay, this is the count.
Okay, so this count and this count is a vector, and also the input we are seeing the value, right? The
Yeah,
load
load value. Yeah, it
value.
should be a vector.
Okay.
Yeah. Okay. So let's start Vivado. Started. Okay, so we create a project. First, we'll create a create project. As we know, we can give a universal counter. Then add the project. The next, any device we can choose, and then finish. Add source. Sorry, not add. Create file. We know, right, what ports we want. We already right now. You can write clock in STD. Then we know, right? We can design any active high reset, right? Last time so let's say we designing active high. Okay, we can comment it active high. Also, clock is also we are designing rising edge.
Rising edge. Okay.
Design rising edge only. Okay, because now it's a counter, right? So it is like why we need clock, because every time it has to store the previous value and then generate a new value, right?
Yes.
That's why we need a memory. So to have a memory, we should have a clock to store the right. We need a flip flops, and flip flop needs a clock. Okay.
No.
Then we have a load. Okay, load enable. So when one, you can comment it like when one it loads value in counter. Okay. Then we have a enable counter. Okay, counter enable. Counter enable is like when when it will enable the counter to increment or decrement. Okay. Then we have a load value. Load value. So load value is same size as the counter size, right? So let's say we are designing a 4-bit counter, count to 0. Okay. Then we have increment or decrement, right? So increment, decrement in so 1. Okay. And then output count. 4-bit counter, right? So okay. So now ports are done. Now let's design the counter. Okay. So definitely you remember, like it's a sequential circuit, and to use a clock we always need a process. So sequential circuit should always or must always write inside the process. Okay. And the process must have a, and we want change and is active high asynchronous reset, right? Asynchronous. Synchronous reset, why we are choosing, like we can without a clock we can reset the counter so that anytime we can reset it. So that's why are using asynchronous reset. We want change on the change of the counter to be sensitive to the clock and reset. So we must use the clock and reset, no other things inside the process. Okay. Begin in process. And also one more thing, like there is a label also. We can give a label also process. So I'm not giving label as of now, but you can give a label also, like count process, count P, and label like this.
Okay, okay. So if there are like multiples, then we can put label.
Multiple process are there, so when in like when in the like means it will be easy to like, not easy, basically it will help you to
Yeah.
like identify which process and all, but not definitely not in simulation. Only the visibility in the code, nothing else. Here it didn't. Reset exactly right. So take one. Then at reset, we always initialize the value output. So there's only one output, right? So we initialize that output. And how we can make it zero, all bit zero? What we should write?
Others 0.
Yeah, other zero. I remember. Then else if so it's a rising edge, so we write clock to 1 and clock tick event. Then okay. So what? Okay, following on it. So now we write the actual design here. So this is like a basic register or register initialization. We did counter initialization, and now we have to write how should increment, decrement, or whatever. Okay. So first of all, when the counter is enabled, so we can do a load, right? We can do any time load in the counter. Okay. So the load should be a top priority, highest priority. Then highest priority means like in the if we should have a first like I remember, right? If is a priority encoder, right?
Yeah.
So whatever the first statement will be there, it will be executed having a priority, and it will be executed always when it's a true. So first of all, we want to have a load highest priority. So we should use a load first statement. So load enable equal to 1. And then we should load the counter with the count load value. Okay. Else what we should do? Else basically else if we can say, okay. Else if other condition next we want to increment or decrement. So basically to increment or decrement we should have a counter enable. Without counter enable, see, right, it will enable the counter to increment or decrement. So this should be a next counter enable equal to tick 1, then count gets, and then when is then what we should do? We should increment or decrement, right, in this condition. So now when to increment, or here in this condition increment or decrement. So, so to choose increment or decrement, we should have again if inside this. Okay, this. So if increment decrement equal to tick 1, then count gets count plus tick 1. Okay, it's incrementing. Else it should increment. Count gets count. Okay. Now it's saying error, right? Why error? Because the we have not used the see the plus object cannot be determined. So basically we have to use a library. Basically library is there attribute, but package the unsigned package we have to use. Oh, okay, one more thing. This is output, right? So output we are reading, right? So we cannot read the output, okay? In the this is output. So we are reading in, right? So we cannot use it as a uh, basically this is not visible to read inside. Okay, it's always going out, so we cannot use it. So we have to use some internal variable, or we can say signal. It signal count in, basically we can say internal. Okay, the same size std underscore logic. Three, then we can rename it to int. Okay, now this int we have to use means count. You have to connect to the count, right? Count is output. So this output, this value should go here, right? So we can do count equal signs to count int. Okay, so this value, if so, you can say, right, why we are not writing count here itself, right? In the here, so it will, right? We can write same statement here, right? You may think,
Mm.
right? But what will happen? It will, it's inside the clock, right? So it will add another pipeline in between, basically one more. Uh, I'll say, tell you like so. So let's say this is count int. So if let's say we are using this in the process, what will happen? There'll be a register created, H, and then this will be a count. But we don't want like this side. It will delay one more cycle. It will take extra.
Yeah.
So instead, we will directly connect from here to here. So we should, so to connect directly, we should use like
Outside
we
of
should
that.
outside of the clock basically.
Okay.
So either you could write like this also. It's the both way we can write process and then begin and end this, and then you should have a count enable count it here, and okay, and basically this. We can choose to write both, anyone. So both are having same hardware, same simulation, nothing, no difference basically. You can do either this or this. No difference in the hardware, no difference in the simulation also. It's doing the same job. You can write outside also, you can do in the right in the process also. Okay. So but since it's a simple assignment, there is no condition directly you can write outside. It's just a connection. Okay. So let's see what it's doing. Okay. Can elaborate it. See. You see what is doing. So remember there's always a register between the count. Okay. So there's a register is there for see that a register showing like 4 registers are there. Okay. And each register is that is connected to the count. Okay. And the same count. This is basically int count int, and the same count int is used either to add or to minus. And based on what? It's like a one input. So it is either decrementing or incrementing. Okay. So this is one basically plus one or minus one. Okay. And then it is doing what? And then selecting based on the increment decrement. So if it's a one, we select basically the plus, the best select minus. And then I say, "Well, what is the highest priority? Highest priority is a load. Okay. So that's why it's the next statement. So when this is load enable is one, it will not take this one. Okay. It will take always this one. Okay. And then you see it will basically load the value here. Okay. T.
Yeah.
And what is when the count is enabled, it will increment, it will yeah, so count enable, there's a count enable is also there basically. So when the count enable is there, it will load the output basically. It will enable the counter to increment it. Okay. So value will be either this, but enable will be on when the counter is enabled.
Mm.
It will choose either 0 or the counter enable. Okay. When the load enable, so basically it's like a highest priority. So you see, it's connected to the load. So when the load enable is there, it will always be load enable is one. It will not use the count enable. Basically, it will use the one. So counter enable will be one. When the load enable is a counter enable, these registers are enabled. Basically, C is a enable register enable. So this will go as a one, and it will always be enabled when the load is there. So that it can load the value, whatever load value is coming, irrespective of the count enable. And when the load value is 0, it will check the count enable. When the count enable is 1, then only it will take the new D. Basically, new D, it will load it. New D can be either +1 or -1 or the load value. Each cycle. Okay. So let's simulate it. So we can directly instantiate the counter. Okay. Is a component. And we create a port map. And nearby some police station or
No, no. Actually, in New York, it is always like that.
oh,
Some cops or some ambulance.
always.
Yeah, always something happens here, so they keep
It's so
running.
crowded. So it's like
Yeah, it
always
is
something.
crowded, and also always something is more crime related or something happens. So that's why we are more police.
A lot of crime is there.
Yeah, a lot of crime is happening nowadays.
Okay. And now, so its error is there because we did not declare the signals. So let's declare the signal, same signal we want. Signal.
So the sequence doesn't matter, right? I can move this.
Yeah, yeah. So when you so when so there's two way of I'll just tell you there's two way of port map. So one is like this one, okay? So
Yeah.
it does not matter what this sequence and this sequence, it does not matter, okay? But there's like a, this is called named port map. Named, okay. One is positional port map, okay, which is look like this, okay. So you will not be having this side value. Only one will be there, okay. One variable will be there, which is local to uh, your in the named. So this is called position map, positional port map, okay. That's it. Okay. So it's declared already. That's why it's comment. Okay. So what is position? This is named port map and this is positional port map. So positional port map will the same position should should match the local signal. Okay. So
Okay.
what it means like currently we are using the same name, right? So you see, so but this represents the local of the test bench. Okay. Here
Yeah.
and if let's say I do clock here and count enable here. Okay. So it's still no error, right? But what happens like this count enable is connected to the clock of this port.
Okay. Okay. It's
Okay. So this is local to the test bench, and the local test bench count enable signal is connected to the first signal of the port of the this. So what is the first signal? Clock. Okay. So it's always like there's a so to have a confusion or better readability, we mostly use an like named port. You can
mm,
use this also, no problem, but there's no readability there. Which signal is connected to which one?
okay.
Like you cannot read it basically. So but there's a both two-way port map. Okay, so let's know this. Understand this one.
Yeah.
And this anyway this is local to the test bench, right? So however you write does not matter.
Mm, okay.
So now we have connected the port map. So now we drive the signals, right? So we generate the stimulus. So what we have to we have to generate all these values, right? So let's say we initialize it. Okay, some value. Let's 0. Then it's a active high reset, right? So we want reset to be high beginning. Okay, so that it can initialize the counter internally and load in. Let's say everything is 0 at the beginning, and then we load value should be others because a vector, right?
Yeah.
We never initialize this way in the design. Okay, this test bench we are initializing this way, but don't design in the like here anywhere to initialize it. Okay, these are ignored in the synthesis. There's no hardware for this kind of okay generated, so it will be ignored. So there's no initialization will take place when the hardware is created. She should not use this kind of initialization in the hardware. Basically, you could test bench, you can use anything, no problem.
Okay.
This I'm telling in between like something related to synthesis. Why it's important? Like you should always your intention is what? Your intention is to write a code which generates a good hardware. Okay. So that's why these are important. Synthesis is very important. We should know like what it's going to generate hardware. And that's why I'm always showing you the semantic so that you can understand the semantic, what is happening. You understood this part?
Yeah, I got it. The
Load
increment.
and load and count enable. Load and count. This you would understand. Load and count enable. So why load is connected here? You see, this load enable is connected here. Why?
So basically, that these two, if you see the first mux that is giving going to the D, and second
Yeah,
mux is going to the that
the
is enable.
yeah,
So
enable.
it will enable or disable that
Yeah,
count.
yeah, enable or disable. But so when it should so when the load value is there, basically when the load value is selected, basically when this is one, it will select the load value. Okay,
Yeah.
so load value will come here, and load value should always load irrespective of the count enable. So you see that when this is one, basically when the load value is one, it will select this one. Okay,
Yeah.
and then this means like it will always load this value. This is one because always enable.
Enabled.
And when the load value is zero, it will select this count enable. So based on the count value, it will increment or decrement. The increment will like this path will be selected,
Yeah.
and this is either increment or decrement value. Okay. So that's why I'm saying like you should always try to understand what you have written
Okay. That's
and
step.
generating similar code or not. At some point of time, the code will be very large, and seeing schematic is like it will be like you can see it, but to debug it, but like very big schematic will be there, and you cannot really understand. But you can still understand. That's not a problem. You can go and go in a small piece of code where your code is going. So that's why it's like always better to talk about the synthesis in between also, like what we should do, what we should not do.
Yeah.
So I've already told how we can generate clock. Clock is always not of clock after half of the period. So let's say 5 nanosecond. You say. And now first is reset, right? So first thing we have to do counter, we have to release reset. Currently is a reset. One is reset. Okay. We have to we should release the reset. So reset gets initially it's one, right? So anyway, one, then wait for let's say 100 nanosecond. Anytime you can give reset. Let's give a some odd time because 91 maybe. Okay. So that you can see the edge of the clock and reset is different time. Otherwise, you see, so both are happening same time. Okay. Since it's a synchronous, we can see it. Okay. Because 91 will not never fall right on the edge because this is always 10. Okay. So it will always happen at 5, 10, 15, 20. So 91 will never fall on the same edge
90.
rising up. So we can see the reset is going low at the edge, which is there's no edge basically, no clock edge. Okay. Now again we wait for some time, let's say 100 ns, and let's say increment also. We do increment count enable basically, and then we did load here, load enable, and then load value. Load value can be let's say 5 we are loading, not 5 maybe we load. Okay, and then again wait for 100 ns. Then we do load.
The load value we mentioned it as a 4-bit.
Oh, 4 bits, sorry. So 7, so 0, 1. Then we do and then we do count enable 0. Then again wait for then we do count enable 1, and then increment decrement now. Okay. we made 0. Okay. Already there. Let's run this much of. Okay, we can extend the stimulus if you want later. Okay, so let's let's see here. We'll zoom it. So first I am releasing the reset here, right? Okay. So you see before the clock edge I am releasing the reset. And count. So basically the count enable will take place. Okay, count enable is taking place here, but it's not incrementing here, right?
Yeah, that is asynchronous.
Yeah. So increment decrement is while. So then we do increment here. Decrement, right? So we should increment here. Okay. Otherwise it will remain same. Can rerun again. See, so it will always increment at the edge only, right? Because so even the count enable was 1 here, but there was no clock edge here, right? So it will do from here, okay? Which is like the clock basically, okay?
Yeah, the
The
rising.
clock, there's a rising edge clock is there. So what increment decrement was 0, right? So it is decrement. When this value is 0, it's decrementing. Let's make it decimal, okay? So after 0, it's like decrement, like it's a overflow, right? 15, 14, 20, and then 6, okay? But you see, at 6, we suddenly make the load enable, okay? High. So load enable takes priority on the count enable, right? Because load enable is first statement. So you see, whenever load enable is there, and then when it samples the next clock edge, where is the 1, it loads a value which is 7, okay? It's loaded. It keep loading until it's going 0. So here it goes 0, but there was no clock edge. Nothing will happen without clock edge. At this clock edge, it sees like again count enables, but increment decrement was 0, so it's decrementing, right? 6, 7, 8, 9, 10, and then 0 again, 15, 14, 13.
This
Okay,
this part I didn't understand. From 7 to 6 it decremented. Then it comes to the 7.
because we are loading, right? Load enable is there, and load value was what, 7. We loaded on the counter, right? The new value, this code. So when load enable is there, counter will take the load value itself, not increment decrement.
Yeah.
So what is the load value? 7. So when the
No.
load enable is 1, then counter enable is does not matter because it's a priority, right? Priority encoder. You see the first schematic source. Schematic is closed up. Leave it. Yeah, here. So you see the first does not matter. So whenever the load enable is there, what is the value of the counter? This O value. It is a load value, right?
Load
It's
value.
this. So load value is this value it will not take. It will not load in the register. It will load the load value. So that's what it's loading.
On this schematic, it doesn't do any simulation there. Like it doesn't.
No.
It doesn't
We can
show.
see now. Now we are putting here, right?
Yeah.
Okay. So let's try in the schematic. Basically, it will not show. Yeah, it is not showing schematic. But here, yeah, here it does not show. Okay, so in this you understand now, right? Because the load enable is high. See, load enable is 1. Okay, but count enable is also 1. But it will take the load enable on the priority, and it will do the load enable part, not the count enable. Okay, so it will, until the load enable is 1, it will load the value in the counter, which is 7. Okay, keep loading. Okay, and once the counter load enable is going low, and then the count it sees then the count enable take the priority, and then it sees the count enable is 1, and then again started decrementing. Okay,
You
and
said.
yeah.
Sorry, you said that till when it is decremented to 0 from, and when we try to decrement 0, right, it goes back to 15.
Yeah, because rollover, right?
So
If we
how does that happen, like this, that rollover?
So basically it's a 0 minus 1 is what?
0 minus 1, 1,
Is a
the,
minus 1.
yeah, I mean the borrow one, and yeah,
Yeah, so borrow 1. So we don't we are not having any carry out, right? Or borrow out. So what is minus 1? Minus 1 is all ones.
okay, just
And then again. Basically it's a rollover. So it keep from 15 there is no maximum value, right? So from 15 it goes to from 0 it goes to the maximum value, whatever rollover.
okay.
Again keep doing the same thing out. And then here see the count enable goes 0. We stop counting and hold the value whatever on the counter was there, last value. And then again we started count enable, again started decrementing. Okay, but you see we made when the count enable next time we put increment as decrement as 1, so it changed the direction. Now it was doing 14 13 reverse way, right? Now it started doing 13 14 15 and 0 1 2 3 4 5 6 7. Okay, and you see without clock the reset came, right? After just after the clock,
Yeah.
and so it immediately executed. So this part, right? So this width is lesser than this, so immediately it made 0 because a reset is highest priority. Yeah. So so this is like a 4-bit counter, right? Can we make a generic counter? We can make. So let's make a generic counter. Do you remember? We can make it a generic counter also, right? Because we can say, let's say this counter we can reuse many places, right? So to reuse it, we should have a vector size we can override any value. So we should use generic. You remember generic?
Yeah,
We made
we.
add also the generic. Can take 4 here, then Can take this, so 3, right? So width minus 1, okay?
Yeah.
Because we take 0 also consideration, right? So total width is 4, including 0. This also. Okay, now same thing we do in test bench. So we have to do generic map, right? Generic TV count. We go here. Generic. Then we have to do generic map also. Because we can override value from the test bench. So we should do generic map so that we can override it. Generic map in width. This will be connected to the local width, okay? And we can say the name of the local, maybe some count width. I'm just changing the name so that I can show you like we can change the name also. Okay. We have to declare this count width is the integer. Constant, basically constant count width type integer. You can choose any value. Let's choose 5 value, okay? And then here also we have to choose the count width. Here this is a count width minus 1, okay? Because this is a local variable to local signal to test bench. This constant. And then this is a width minus 1. Okay. This one std logic vector, basically two std. So we are making now because we don't know, right, what what value will give, okay? To std logic vector will give 7. I'll tell you next time maybe. So currently we can choose 5 bit, okay? But there's a way. Currently we are choosing 5 bit, right? But there's a way we can choose a generic. So we can convert an integer value to a vector. Okay. I'll tell you next time. So now we change to the 5 bit counter. Let's see how it works. Run simulation. You see, right? After 0, now 5 bit we made, right? So it is 31 maximum value, 31. Okay, rollover 5 bit. And then it goes to 22. Again, we load 7, right? We remember we put 7 value. We
Yeah.
loaded 7 value. And then again decrementing. And after 0, it was going previously 15, right? Now it's going 31.
That load value is not such required, right? We are just doing it to,
Yeah, any load value you can give.
yeah,
Just we are,
if you want to, I mean, put that value.
yeah,
Start.
yeah, any value you can put. Yeah, it does not, there is no requirement. You can put any value.
Okay.
It's up to the user. Okay, then after 39, this again it goes like we made increment. So after 29 become 30, 31, and 0, 1, 2, 3, 4, 5, 7. And then we did reset. Okay, and then reset again doing the same thing. Now increment was high, right? After reset, we did not change the increment. Increment remains high. You see, it's incrementing. And loading 7. Now increment is high, so it's incrementing. Okay. Any question now?
Mm. Can you go to once the that file our